in our simulations, we've seen that in these systems, like in this Swift-Hornberg equation or the modified Korn-Moldau-Sierpyczynski equation, you have a control parameter, and if you increase that above a certain value, a range of wave numbers destabilizes the homogeneous state. And we saw that when we start now with a pattern which is almost periodic, it actually relaxed back to pretty much perfectly periodic pattern. When we start with random initial conditions, we had initially a wide range of wave numbers. I should point here actually, because that's the control parameter we had it running with. And after a short time, these high wave numbers all disappeared, decayed away, because those modes don't destabilize the basic state. And only wave numbers in this narrow range here survived. And the relaxation we observed was actually relatively slow, the final relaxation. And so that's what we want to focus on right now. We want to see whether if there's a slow dynamics that always suggests that there's a reduced description in terms of a simpler equation. And we'd like to see whether that's possible and what kind of description that would be and what we learn about the dynamics of these patterns here. And we find out that reduced description is possible and that slow dynamics arises from the translational symmetry of the system. Actually, more precisely from the fact that that translation symmetry is broken by the solution that we're looking at. So what do I mean? Well, we're thinking of a periodic pattern in this infinite system which is translationally invariant. So that pattern obviously breaks that translation symmetry. But because of the translation symmetry, we can always shift this pattern over by some distance. And that distance is arbitrary, like delta x. And when we shift the pattern over, it doesn't come back. It doesn't relax back because the other position is just as good as the previous position. And the fact that it doesn't relax back reflects that there's a zero eigenvalue associated with the system, with the linearization around this pattern. There's a zero eigenvalue. Whenever there's a zero eigenvalue, then you know there's a time scale separation, and you probably can reduce the description after initial transients to dynamics associated with that zero eigenvalue. So how does that help us to describe this relaxation of different wave numbers? These patterns here were meant to be just strictly periodic. Well, you can imagine that we have a pattern and we shift it. But in this case, we don't shift it the same amount everywhere, but rather we shift different amounts. So that will lead to compressions and expansions. You know, say, for instance, like maybe I shift it to the right here. And here I don't shift anything. And here I shift to the left. And here I shift even further to the left. And here I don't shift it more to the right. As we see that if I compare the positions, this wavelength here has become shorter, as has this one, whereas this wavelength has become longer. So I have an expansion and I have a compression. And what we're interested in, what is the dynamics that result now after this initial condition? And the idea is that if we make these compressions and expansions on a very long wavelength, then it's almost as if we were pushing the pattern uniformly everywhere, almost. And if it's almost like that, then that eigenvalue that is zero when you do a rigid movement, that eigenvalue will be small, and small means slow dynamics. So that's the idea. So let's see how that works in a concrete system. And let's just first identify that zero eigenvalue and its eigenvector. And for that, let's take the Swift-Hornberg model. So we have our Swift-Hornberg model, d psi by dt is equal to r psi minus d by dx squared plus 1 squared psi minus psi cubed. And I know I have a solution psi of x. Then I also have a solution x, psi of x plus delta x. And that's for any delta x, right? That's the important part. It's a continuum. If it's a continuum, then I actually can take the equation for my steady pattern and take a derivative with respect to that shift. Well, let me say what I mean. So we're looking for steady solutions of this equation. So let's write that down. So the steady solution will be r times psi. And I'm allowing myself to not just take the solution at x, but a shifted solution is just as good. So I have then this equation, the other term stays the same, but also with a psi that is shifted by delta x. And then I have psi of x plus delta x cubed, and that is equal to 0 because we have a stationary solution. Since this is valid for all delta x, I can now take a derivative with respect to delta x. And obviously, the derivative with respect to delta x is the same as the derivative with respect to x. So that means I get, when I take the derivative, I simply get psi prime here. I also get a psi prime here because I can pull the derivative across these derivatives. And here I have to do chain rule. And let's see what we get. So we get, therefore, r. Then we get minus d by dx squared plus 1 quantity squared psi prime of x, right? When I take the, well, actually it's psi prime of x plus delta x, but that's really immaterial. And finally, we need to still take the derivative here. Well, that gives us minus 3 psi squared of x plus delta x times psi prime of delta x, x plus delta x. So we see that we have here a linear operator, L, and we know that L times psi prime is actually equal to 0. That means this operator is singular because there is a 0 eigenvalue. So L is singular, and that is that 0 eigenvalue that I was referring to earlier. And that 0 eigenvalue is associated with what's called the translation mode, which is the derivative, which is related to the fact that we're shifting the solution. Okay, so that's the zero mode that we're talking about. And so now we want to see how we can actually implement a perturbation calculation exploiting this 0 eigenvalue. This will take a little while, and we'll rather take a different equation where we actually also have exact solutions. So instead of the Swift-Hornberg model, let's take our Ginsburg-Linda equation, where we get exact solutions for the, at least periodic solutions, and that will make life a little bit easier. So we have the equation dA by dt is equal to dA by dx squared plus mu a minus a absolute value squared a. So that's our Ginsburg-Linda equation. Okay, so the goal here is that we want to look at periodic solutions of that equation, which we know exist. We've calculated them before. And then we want to modulate those as we want to modulate the wave number, and we want to do that on a long space scale. And because long wave modulations will decay slowly or evolve slowly, associated with that near zero eigenvalue, we will get slow response. So we need to introduce slow space scales compared to what we have already. So meaning we want to have super slow space scales and time scales. So let me actually call these time scales here, therefore, write them as if they were fast, because we're going to introduce super slow ones in a second. So that's our Ginsburg-Linda equation. Okay, so these shifts essentially amount to changing the phase of the pattern rather than the amplitude. And therefore, it's better to write the whole thing, or at least look at it in terms of amplitudes and phase. So let's write R as the magnitude. And so if A is equal to R times e to the I phi, if we plug that in and separate real and imaginary parts, we get two equations. We get dr by dt is equal to d2r by dx squared minus, and so now you get actually a d phi by dx quantity squared times r. Well, that comes about because when you take the second derivative of this, well, first you get two derivatives on this guy, and then you get 2 times this derivative times this derivative. That's an imaginary part, which will be in the other equation. And then we get once the second derivative of this thing, which brings down I phi prime squared, which is this thing. Okay, and then finally we have our mu r, and we have r cubed. And we have for the phase, we get an equation which first is just d phi by dx squared. And then we get this term that I mentioned before from this mixed mixture of the derivatives here and here. So that's d phi by dx, dr by dx. And there's an overall factor of r, and I'm going to put that down here. So I have 1 over r here. Okay. So we have now the equation for the magnitude and the phase. So let's first just look at periodic solutions. So periodic solutions in space, meaning stationary in time and space. So it's easy to see that you have a solution r is equal to square root of mu minus q squared. When phi is equal to q times x. You see, like if phi is equal to q times x, this is just a q squared, and you have a mu minus q squared, and the magnitude is constant in space and time, and so that's our solution. And of course, that's just, again, capturing that on the neutral curve, which is mu equals q squared, the amplitude goes to 0. Okay. The idea now is that we want to allow this wave number to vary in space. And so let me rewrite first this equation for the phase in terms of the wave numbers, just to get a better feeling for what this slow dynamics comes from. So I have a d phi by dt is equal to, so q is actually the derivative of the phase. I'll make a comment about that in a second, but let's first just note this down and use it. And so we have actually first a dq by dx plus 2q 1 over r dr by dx. And so now it's very clear that if the wave number is constant and the magnitude is constant, then obviously the phase doesn't change and the pattern doesn't evolve, it just sits still. But if you now modulate the wave number on a long space scale, meaning the gradients are small, similarly the magnitude gradients are small, then you see the phase evolves, but evolves slowly. And this longer the wavelength of this modulation, meaning the smaller the gradient of q, the slower the phase. So that's the point, why we get a slow dynamics. Good. Let me get back to the statement here that q is the derivative of the phase. You could have thought, well, we have phi simply q times x. And if I allow now q to be depending on x, then I would simply get phi is equal to q of x times x. That looks at first convincing, but it's actually wrong. And it's wrong because what is phi? Phi essentially evolves always by 2 pi whenever you cover a wavelength. And so if you look at the picture, if you go from here to here, the phase evolves by 2 pi, and again by 2 pi, and so on. So that means the phase here tells you how many wavelengths are to the left of that position. And so the phase does not simply depend on the wave number right here, but it depends on the wave number everywhere to the left. So it's actually the integral over q, or in other words, q is the derivative of the phase. So let's write down in terms of the integral we have. The phase is the integral of q of x prime dx prime. So that's our phase. Good. So we want to allow now slow variations in the wave number. Good. So we want to have q a function of some slow variable in x and t. So there are different ways to deal with that. I'll choose one which is sort of similar to the WKBJ method in some ways. So what am I going to get? Well, I want to have a phase. I want to get an equation for a phase. In that phase, I want to depend on a slow variable x and t. However, the wave number itself is not small. Now, the phase is the gradient of the phase, and therefore there's an issue in terms of when you take the gradient with respect to a slow variable, you get always small quantities. Well, let me just do it and then you see what I mean. So we're going to introduce a new phase, which is phi, no, that's the, I'm sorry, the phase we have, and we write this as 1 over epsilon times capital phi. And the capital phi depends only on slow x and t. And let me be concrete. I'm going to pick x equals epsilon x. Well, that I can do as I please. That's my first choice. I mean, my first choice for a small parameter. And I'm picking t being epsilon squared t. That is motivated by the fact that we found here a diffusive kind of equation for the phase. And so it seems like we should scale t diffusively, like with an epsilon squared. Okay, so once I choose this phase, and I'm looking now what is q. Well, q is defined as the derivative of the little phase with respect to little x. And if I plug that in, that's 1 over epsilon times the derivative of capital phase. But the capital phase, phi, depends on slow variables. So I have 1 over epsilon times d by d capital X times epsilon of capital phi, or simply d capital phi by d capital X. And so indeed, I have a wave number which is order 1, even though I've generated from a phase that depends on a slow variable. But it's because of this 1 over epsilon that I get it to be order 1. However, the derivative of q with respect to x, that we want to be small because that's supposed to be slowly modulated on a large space scale. So therefore, let's look at what that is. That would be d by dx of q, which is d capital phi by d capital X, which of course is epsilon d by d slow x capital phi derivative. And so you see that this is indeed order epsilon. So the gradients in the wave number are order epsilon, but the wave number itself is not. And so that framework will be suitable. And so this is similar to WKB approach because the phase shows up for our complex amplitude here. And so when we plug in our capital phase, we actually have now, with this ansatz, we actually have A is equal to R times e to the 1 over epsilon I capital phi. Okay, good.